Close your eyes for a second. Imagine you're floating in space. No gravity, no sound, just darkness. And billions of tiny little stars stretching in every direction. Every single one of those lights, it was born. It lived, and someday it will die. We are going to follow that story from a cloud, invisible gas cloud, to one of the most violent explosions in the known universe. And here's the twist: you are a part of that story. Welcome to the life cycle of a star. Let me give you the roadmap before we zoom in. Every star follows this path: nebula, protostar, main sequence, red giant, and then it gets interesting. Depending on one single factor, its mass, a star either goes out quietly like a candle or it explodes with the force of a trillion nuclear bombs. Low mass stars fade gently, high mass stars go out with a bang. Keep this map in mind in your head. Let's now take it step by step. It all begins with nothing dramatic, just a cloud. A nebula, from the Latin word for mist, is an enormous cloud of hydrogen gas, helium, and cosmic dust. We are talking hundreds of light years across. To put that in perspective, one light year is about 9.5 trillion kilometers. The nebula is, quite literally, incomprehensibly vast. So, what wakes it up? A trigger. Usually a shock wave from a nearby exploding star. The shock wave squeezes parts of the cloud together. Denser regions start pulling in more gas through gravity, and slowly, inevitably, a collapse begins. The star has been conceived, but it won't be born for thousands of years yet. Fun fact, have you heard of the pillars of creation? That iconic Hubble Space Telescope image? Those giant pillar-shaped structures in the Eagle Nebula, those are actual stellar nurseries. Baby stars being formed right now as we speak. The collapsing gas cloud forms a spinning disk, and the core keeps getting hotter and denser. At 10 million degrees Celsius, something magical happens. Nuclear fusion ignites. Hydrogen atoms are smashed together so hard they fuse into helium, and this release enormous energy. The star begins to glow. It begins to shine. A protostar is born. Now here's where it gets really elegant. This baby star is in a tug of war. Gravity is trying to crush it inwards. The radiation pressure from all that fusion is pushing outward. At some point, these two forces perfectly balance. This is called hydrostatic equilibrium. And when a star reaches it, it settles into what we call the main sequence. This is the adult phase of a star's life. Our sun has been in this phase for 4.6 billion years and has about 5 billion years to go. But a massive star, say 30 times the mass of the sun, it burns so bright and so furiously that it exhausts itself in just 10 million years. Mass is equal to fate. Remember that. Eventually, the hydrogen in the core runs out. The fuel is gone. Without the outward pressure of fusion, gravity wins temporarily. The core collapses inwards. But the outer layers, they expand outwards enormously. The star becomes a red giant, swelling to 100 times, sometimes 1,000 times its original size. Here is a mind-bending fact. Our sun will one day expand so large it will swallow Mercury and Venus and likely scorch the surface of Earth. Don't worry, that's 5 billion years from now. Meanwhile, in the collapsing core, temperatures get so extreme that helium begins to fuse into carbon. The star has found a new fuel. For massive stars, this process continues. Carbon fuses into oxygen, then neon, then silicon. all the way up the periodic table until the core is full of iron. And iron is the poison of the stars. Unlike every other element, fusing iron absorbs energy instead of releasing it. The star's engine stalls, and what comes next is spectacular. Now we hit the fork in the road. Two paths determined entirely by mass. Path 1, low mass stars like our sun. The outer layers drift away gently, forming a beautiful glowing shell called a planetary nebula. What's left behind is a white dwarf, a dense Earth-sized lump of carbon that slowly cools over billions of years. Eventually, it may become a black dwarf, a cold, dark ember. Interestingly, no black dwarfs exist yet. The universe isn't old enough. Path 2, high mass stars. The iron core collapses in less than a quarter of a second. The outer layers slam into this rigid core and rebound outward. In the most violent explosion in the universe, a supernova, what remains could be neutron star or a black hole. Let's look at both. A supernova is almost incomprehensible in scale. For a brief moment, a single exploding star outshines an entire galaxy. 100 billion suns worth of light. The explosion releases energy in seconds than our sun will ever in its entire lifetime. The shock wave tears through space at 30,000 kilometers per second, 10% the speed of light. And here's the beautiful part. All those heavy elements forged in the stellar core, gold, silver, platinum, uranium, get scattered across space. These become the building blocks of future stars, planets, and life. What remains at the center can be a neutron star, the most extreme object short of a black hole. A teaspoon of neutron star material weighs 1 billion tons. Some neutron stars spin 700 times per second, beaming radiation like a lighthouse. We call these pulsars. And a personal favorite fact, the gold in your earrings, the silver in your jewelry, it was forged in a supernova billions of years ago. And if the remaining core is more than 3 times the mass of our sun, not even a neutron star can survive. Gravity crushes it further beyond all known physics into a singularity, a point of infinite density, zero volume, and surrounding it a boundary called the event horizon, the point of no return. This is a black hole. Nothing escapes, not gas, not light, not information. Time itself slows down near a black hole. If you were falling towards one, an outside observer would watch you freeze at the event horizon, stuck in time forever. In 2019, scientists photographed a black hole for the first time. The M87 star, some 55 million light years away, 6.5 billion solar masses. And at the center of our own Milky Way galaxy sits a black hole called Sagittarius A star, 4 million solar masses. It's there, right now, quietly anchoring our galaxy. Here's the part I want you to remember long after this lecture. Every atom in your body, the hydrogen in your water, the oxygen you breathe, the carbon in your DNA, the iron in your blood, was made inside a star. These atoms were forged in stellar cores over billions of years and then scattered across the galaxy by supernova explosions. They drifted through space, were pulled together by gravity, formed a solar system, a planet, oceans, life, and eventually you. Carl Sagan said it best, we are a way for the universe to know itself. The universe didn't create stars for us, it created us from stars. So let's recap our journey. nebula, protostar, main star, main sequence, red giant, supergiant, supernova or planetary nebula, white dwarf, neutron star, or black hole. Now I want to hear from you. Think about these. What is hydrostatic equilibrium and why does it keep the sun stable? If our sun were 20 times more massive, how would this story change? Thank you.